I guess we can start. Good afternoon, everyone. This is the Bess working group session in Seoul, and I am alone, so don't take the opportunity to beat me. Note well, well, you know it, but please pay attention each time you see that and be aware of its content. Blue sheets. Sorry for that. Any volunteer for Jabber to help me? Or some minute takers? You'll take, yeah, okay, that's great. Quick reminder that there might be a virtual queue. There is a virtual queue. I don't know if it will be full or not. Just in case there are some discussions, keep this in mind. And I'll try to manage that as well. Quick summary of the working group. First, we'd like to thank the 5 volunteers for the shepherd's role. We've had a few. And there are further opportunities for that as drafts come and go. So don't hesitate. We have a new RFC since last meeting. We went through 2 working group last call and adopted 2 new working group documents. Result of that is that since the beginning of the year we tried to push a bunch of documents through last call. Result is that now the queue is going on our side. So we have 6 of them. I know Ali is a bit for valid reasons, honestly. So there are 2 of them that we really need to move forward. We as chairs really need to move forward rapidly. They are the first 2 ones. I think VPWS is in the hands of our AD. I'd like to say a few words on the MIBs. So we had Jeffrey who had volunteered to finalize the work. However, he had to leave that on the side for valid reasons as well. We were looking for somebody willing to take up the work and finish it, and especially integrate a bunch of reviews from MIB doctors. We have a candidate that has shown a willingness to take up the whole work. We still need to do some discussion with him, but we encourage that, and so that might be a way to close those 2 documents. Final one, virtual subnet fib reduction. It went through last call, but you might remember that we've installed a policy for existing implementations before moving to IESG. There is no implementation, we haven't heard from the working group of any existing implementation. So following the policy, I have polled the working group for support to submit to IESG even in the absence of the implementation. And honestly, the working group was completely silent, except from the lead author. So on today, unless I hear strong opinions on the list rapidly, I'm inclined to put this on the side until I know of an existing implementation. So the queue on the chair's queue is pretty full, but the working group queue is becoming empty. We have two documents which I believe are ready for working group last call. and we don't have any in the adoption queue. I'm not pushing for that. Of course, we'll fill that up as when and if documents are ready. But it means that I think we can absorb few ones in the near future. A few heads up. A long, well, as you can see from the title, draft IETF layer 3 VPN. This draft has been hanging out in the wild for some time because there were the main author were not so much interested in addressing the last documents, the last comments that came in that document. And after a long search for an editor, Stuart has volunteered. So, well, we haven't heard from him recently. Maybe he was taken by other subjects. But we expect that draft to be updated following the different reviews that came in and to close this item. And just a heads up also on some working group documents that have expired. They are pretty much the same than last time. So we, at some point in time, will need to take a decision. I think the few ones are just recently expired, so I don't have any fear on those. Agenda, it doesn't exactly look like the one that was posted or that was shared on the list. I simply updated it because we have one slot which was cancelled from Jeffrey. He missed the submission deadline, so he decided not to present, even if material was pretty much ready for that. So it means that we have time for discussion. I'll keep an eye on time, but I won't be strict if the discussions go on. And I'm done. And Jorge, I think it's your turn.
Good afternoon, everyone. Jorge Rabadan, Nokia. This draft is EVPN prefix advertisement. This is the revision 3, and this is the list of my co-authors. Next slide, please. So the draft has been around for 3 years, and basically it describes the route type 5. It's called IP prefix route. And it basically allows the exchange of IPv6 or v4 prefixes in EVPN networks. And you have the format here. And the key thing is that because the draft has been around for a while, now there are multiple implementations and even multiple deployments, not even in data centers, but even in other environments. Next slide. So what did we change in revision 3? So there was this section 5.4 where you have the description of the IP verb to IP verb model, and it was kind of foggy. So we decided to rewrite the whole section. So now is pretty, in my opinion, now is much better. It has been clarified, and also it is also aligned with the existing implementations in the field. So the section divides the use of the route type 5 in 3 submodels. The model 1 is called interface-less model. The second one is interface full with core face in IRB, and the third one is interface full with a numbered core face in IRB. So the 2 first models are required, and the third one is optional. Next slide, please. So the first model, interface-less model, is pretty straightforward. So you have, for instance, 2 NVEs, NVE1 and 2, And the requirements here are basically you have an IP verse to IP verse connectivity, and you need inter-subnet forwarding among the IP verse. And those IP verse are connected directly by NVO tunnels or MPLS tunnels. And those can be Ethernet or IP. And what I mean by that is that Ethernet tunnels are typically VXLAN or NVGRE, or even MPLS over GRE with Ethernet payload. Whereas IP tunnels are, for instance, VXLAN GPE or MPLS over GRE with IP payload. So you use those tunnels to interconnect the IP verse. And the procedures are the following. So if you have a bunch of subnets on MVE2, basically you send the route IP5 per subnet, along with this gateway IP0 and a router's MAC extended community, where you encode the MAC address of the PE. So at the ingress PE, basically you import that route, you put the route in the routing table, and you use all the information coming in the route IP5 for forwarding the packet. And that includes the PGP next stop, the tunnel, and you take from the router's MAC extended community the inner destination MAC for the Ethernet payload. So that's model 1. Model 2, next slide. It's interface full with core facing IRB model. So this is typically the case where you have a core MAC verse or a core EVI interconnecting the IP verse. And what that means is that in that core EVI, you may have Ps or MVEs without IRBs. But when you want to exchange prefixes between MVEs that are connected to that core EVI, basically what you have to do is you send, again, a route IP5 per subnet that you have. But in this case, you will use the gateway IP field in the route IP5 to encode the core facing IRB IP address. And what you send us as many route IP5s as subnets you have attached to the egress MVE or PE. Excuse me. And then you send a route type 2 for the core facing MAC address and IP address. And at the ingress P, basically you import those routes. And when you do a lookup, and the result is basically the subnet coming in the route IP5, what you do is a recursive lookup, which means that you do get all the information, the forwarding information from the route type 2 that is associated to the gateway IP in the route IP5. So in this case, you use the recursive lookup, and this is interesting because it allows you to do this in direction. So you can advertise like thousands of routes type 5 that are associated to a single route type 2. And basically when the egress, if you have redundancy and when the egress P goes down, you just withdraw the route type 2, and you can actually change the the next stop for all the traffic going to the subnets without having to update the routes type 5. And finally, the third model, interface full with a number core facing IRB. It's pretty similar to the previous one. The difference here is that you don't have an IP address on the core IRB, on the core facing MAC verse. So in this case, you still use the route IP5 to advertise the subnets, but your gateway IP will be 0, and you will send those routes with a router's MAC extended community with the MAC address of the PE. And your recursive lookup to the route type 2 will be based on that MAC address. So in this case, there is no IP in the core facing IRB, and but you still do this recursive lookup, but now based on the MAC address. Next slide, please. So conclusions. This is basically the section that was still not clear in the draft. So once it's really clarified, we believe the draft is ready for a working group last call. We believe the draft is pretty fundamental for the development of a VPN, and not only in data center networks, but also in other applications. And I think it's important to take it to last call because it has multiple vendor implementations and many deployments. And that's pretty much it.
Thank you, Jorge. Questions?
Ali suggested Cisco. So I just want to emphasize the fact that this draft has been implemented by multi-vendors and it's been around for quite a while. And as Jorge mentioned, the last point in it was this section which got hashed out over the course of a few IETFs. And that was the only last point was pending, and it is in pretty good shape. And I fully support the working group call, last call for it, and it should be going to the queue right after inter-subnet forwarding, that is being in the queue for quite a while. Thank you.
Yeah, thank you, Ali.
We'll add it to the queue. Himanshu? You're doing layer 2 only?
Yeah, layer 2 only.
Okay.
Do you have the slide?
Yeah, I do.
Yeah. Hi, I'm Himanshu Shah from Sienna, and I will provide the update for the L2VP and Yang model. So we had a little bit of lull between the 96 and 97, meaning this meeting. We've been holding the WebEx design team meeting calls every week, but between this time period, we had a little bit of silence, and I'll go over one of the reasons why. Next slide, please. So we had many comments from the working group, including Giles. I don't know whether he's here or not, but there were extensive comments, and some of the things we had to clarify from Giles, and we couldn't get some time from Giles on the WebEx meeting. So eventually he did attended the WebEx meetings, and we had a significant change in the organization of the Yang data model for L2VPN. So it's good because it simplifies it. What we did is that we removed the VPLS and VPWS instances, the containers in the L2VPN instances, and actually brought all the endpoints into the L2VPN instance itself. So endpoint Z and endpoint A, if you are configuring the VPLS or VPWS, then you define those. Those are now directly under the L2VPN instance. We also removed the VPLS container, and you have a list of the endpoints. So if you want to configure a VPLS, you use the list of endpoints. I think that one of the things we had started the discussion, but we couldn't figure out how to do this in the Yang model, is to further simplify and see if we can even get rid of the endpoint A and endpoint Z constructs. So we can just use the list of endpoints. But if you're doing VPWS, we have you provide a condition so that when you're configuring VPWS, you only have you can only define 2 endpoints. So there was some discussions about that. We couldn't figure out to apply the when clause properly, but we might look into it, and if anybody has opinion or a way to do that, we would certainly like to hear from them. Essentially, we have just simplified the model quite a bit. Next point. Next slide. So the same changes were brought into the state model, the operational state model. We have to add the notification and RPCs. And yeah, we'll continue to address the comments. So we invite the working group to review the doc and provide the comments. I think we need to put this on a fast path and get it done as soon as possible, hopefully by next meeting. So that's the comment I have. I mean, this is the end of it. So if anybody has any comment, I give my extra 5 minutes to Ali for FXC.
All right.
No comment? Okay. You owe me, Ali.
John, is that you or is it? It's no, I think it's
I'm sorry. Voice. Okay.
no, it's not you. So.
Hi, I'm not John, I'm Adrian, and this is a little draft that we've had for a few months and revised a bit on the use of BGP for controlling or operating connection between DC sites in a segment routed world. I guess I have to keep kicking you, do I? Yeah, kick. So a little history. It's turned out to be a really small draft. It's only 9 pages, which really means it's only 7 pages. So go read it. We posted it spring this year and revised it a little bit in the summer. Didn't present it in Berlin because the Bess agenda was quite full anyway. We have recently revised it again with some input from some reviewers and just tidied it up a little bit, but not changed it substantially. So what are we trying to do? So in general, data center sites are well planned, but they have still the need for traffic steering through the sites. And then the sites themselves are interconnected across backbones, which are either operated and owned by the data center operators or by third parties, obviously. And usually the sites are multi-homed onto that backbone. So lots of different protocols within the data center, several protocol options between the data center sites. That's both in the data plane, but also in the control plane. So we might be segment routed, or we might be MPLS traffic engineered, or we might be VXLAN or something. So what we were trying to do was to give end-to-end connectivity from within one data center site right the way through that data center across the core and to the destination in some other site. We wanted to be able to do that supporting all the different data plane options that are around and as much as possible reuse existing technologies to come up with some protocol solution or combination of protocols that would be scalable and flexible. So flexible for all sorts of future developments of what happens in a data center, and scalable because data centers get quite large. And the ease of operation was sort of important. So I think when we started, we thought we might be doing protocol work. And what we ended up with is an applicability statement, really. It's just a pointer to, these are the bits and pieces that exist already in various protocols. This is how you cobble them all together and make a protocol solution. So we're sort of targeting informational. Quick picture, just as a reference architecture. Data center sites can be multi-homed to the backbone. They can be multi-homed to different ASs giving a path across. And this is attempting to be totally generic without being hugely complicated. From that figure, the traffic that might be flowing around splits into three categories. The traffic that's already or is contained inside one data center site is actually, it needs traffic engineering, but it's out of scope for our work, really. Data centers manage their own traffic engineering, we're done. So the two interesting pieces become the inter-DC traffic, that is to say the traffic between the sites, which normally has TE in the backbone, and the choices that are going on there are not just how do you traffic engineer across the backbone, but how do you select the right destination data center site, and how do you select an entry point into that site. And then end-to-end data center traffic, which is navigating all the way through the source site, across the backbone, and into the destination site to the destination. So what's happening there is that the choice of egress, maybe from the source site, depends on the choice of ingress at the destination site in order to get a fully optimal path. So this is we in the draft we tried to decompose what all the choices are that have to be made along the way. So little things like working out where the destination actually is, trying to work out how to get out of the source data center, how to get into the destination data center, and so on. And the decisions are not single point decisions because they reference each other if you want to get a good optimal path. So you can break the problem into these three steps once you've made the choices. So that the traffic engineering can break down, but there's a kind of higher level traffic engineering of choosing the points along the way. Okay. So we have some requirements on the solution, really, that we have to support several different data plane types, several different functions. So if the data center uses MPLS segment routing, then source routes may be computed by a controller, and you might populate the label stack using your preferred label stack population protocol. Or you might have a non-MPLS forwarding data center. You might have segment routing in the data center, but they might not be, the source and the destination data centers might not be in the same segment routing domain. So they don't actually have the same shared view of what the SIDs are. And then the backbone may be a single provider, or it may be multi-provider. And you might have a single controller that can see everything, or you might have a controller for each data center and a different controller for the backbone. And so what we needed to do was come up with a solution that encompassed all of these as options. So that the main component of the solution turns out to be discovery. You need to discover which site a destination is in, which gateway to use to get into a site for that. And we quickly realized this is not very much different from L3 VPN. That is to say, there is a collection of sites that are connected together and the destinations are in the sites. So we looked for a while at the existing proposed solution that the EPE work has had, and that uses BGP add path. And our belief is that, well, that's fine, but it doesn't scale. It won't scale to the sort of magnitude we need for data center. And that's fine. The only thing really to say about BGP-LS, other than it exists, is that it allows you to do summary exports as well as full exports. So in some cases, we're not really interested in knowing the internal topology of an AS we're going to go across. All we need to know is that there is a path across it. So it's possible to kind of decompose the map on the left into a topology on the right. And nothing really new there. BGP-LS just does that. This is more just making the statement that the binding SID can be attached to the to an LSP, and the LSP may be a segment routed LSP, or it may be an RSVP-TE LSP, and it's just a tunnel which has a SID attached to it. And then the controller can put that SID into a label stack and effectively say, when you hit the backbone, oh, that's the LSP I want to use to go across the backbone. So normal processing, segment routing packets, nothing new again. When the label at the top of the stack indicates a link or an LSP, then it tells you where to send the packet, you pop the label, and on you go. A worked example, which you might find easier to follow actually by looking at the slides in your own time. What follows are some slides that say, well, here in the different places in the network are the label stacks you would have. What this is doing is navigating across the source data center from the source to the gateway, and then across the backbone, which happens to be 2 ASs, and then within the destination data center. So let's see if we can make some clarity of that. So what this says is, assume at the source, the whole label stack for the whole path is being pushed on, and these are the labels that you would have for that example, starting, and I won't go through all this, but starting with the way to get across the first data center to the egress of that data center, and then right down at the other end of the stack, you get the SID that's going to tell you, right now you're in the destination's data center, how do you actually get to the destination? Move on. So the options, as I say, you could impose the full source route at the source, okay, which is going to say all the way across the ingress data center, all the way across the core, all the way across the destination. And that's probably the easiest one to think about, and it's just one nice long label stack. But you might have different administrative domains, you might want to share different amounts of data. It's possible that the source data center does not have full visibility of everything, in which case you start using what I suppose you call loose hops. You impose enough labels to get you out of your source data center, and enough labels to identify where you're going, which is the destination data center. And then you leave the border the responsibility to do an expansion to fill in the gaps. And I think that's just standard segment routing anyway. Right, so, and you can decompose that even further and just have very, very vague reachability information and looser hops along the way. So where we are with this, probably the first question is, where should we do this work? I think that this is in the right place because mainly it's focused on talking about using BGP as the tool, but it does use other bits and pieces. So should other working groups care? Yeah, I think we should talk to IDR to make sure they're happy we're not perverting BGP. We should talk to TEAS because it is traffic engineering. The binding SID work is in PCE. And we should make sure Spring is aware. But we wanted Bess to be the first place that we presented this. I don't know if ADs want to comment on where we should do work that clearly spans 5 working groups. But beyond that, what we would like is reviews and comments on the content, and then some hints and advice about whether Bess really cares.
Are you done? Yeah, okay. Jorge Rabadan, Nokia. Related to IDR, the main justification of the draft seems to be that the path visibility, right? That is not enough for this environment. And basically you're saying that add paths doesn't work here, it's broken. So wouldn't it make sense to fix it in IDR?
So I don't think I'm saying add paths is broken. I'm saying add paths will have scaling issues.
But
Now, maybe it's possible to fix add paths so it will scale well enough, and that would be fine and good.
okay, thanks.
In one of your early slides, you think this solution need to take care of the different environment, like a data center. You're not assuming using the MPS but the solution you explained seems like end to end. You have to have an MPS. Yeah.
Okay, so it's pretty much impossible to come up with a set of slides that shows all possible interactions of all possible data planes. So this set of slides presents what's probably the most simple case, which is the MPLS segment routing end-to-end. But if you look at the draft, it basically points out that when you come to a gateway, in other words, an entry or an exit to a data center, you can map, just as you would have to map the data plane, you can map the identifiers.
Okay. Second question, is this a solution only apply to the unicast traffic?
Oh, that's a good question. I think we have not properly thought through multicast. I think it needs to be there probably, but it's going to need, just like multicast in the VPN thing was an entertaining,
kind of
an entertaining addition. I think we do need to address it, but
okay.
Yeah,
I guess I'm next. Even though you need to turn around and look in the back. So I have a clarification question, Adrian, about the advertisement from the destination data center. You mentioned that each gateway, when it advertises a prefix, it advertises all other gateways of that data center that it can be reached, right?
Right.
So my question is, what happens when during a failure, the originating or the source data center gets 2 lists which are different? How would it reconcile these 2 different lists? One of the lists says you can reach this prefix via 3 gateway, the other one says you can reach it via 1 gateway.
Right. Now, hopefully this is a transient problem, because when there's, if for example, a gateway goes down, then it will stop advertising itself, clearly. All the other gateways to that same data center need to withdraw that. So there's
correct, is a transient, but within that transient, how would the source gateway would reconcile?
Well, so this is, I think, traffic engineering, not per packet routing. So always in traffic engineering, we've had this thing of the traffic engineering database on which you are performing a computation might actually not be completely up to date. So you do have windows like that, and you have to correct, just as like when the thing goes away. So
so basically, eventually,
yeah, and I think eventually,
I
think eventually is quite soon. We're not talking
right
hours or weeks here.
Yeah.
So the window is if I am making a new computation, to pick a new label stack to tell somebody to impose, and I make that computation in the window, in the failure window, then I have a concern. And probably the best thing, this is a controller implementation question really, but if you look at it and say, well, I've got a mismatch, okay, either something's coming or something's going. And you could optimize to say, well, I'll just take the smallest set and be safe, or you could say, well, I'll come back in 30 seconds and see what the
Exactly. I mean, whether you run a timer or whatever, and if you needed to run a timer, maybe this kind of clarification needs to be mentioned in the draft.
We can look at that. I think we're trying not to specify too much how a controller would actually be coded. Okay. Jeff.
Jeff Tensura. Given the amount of information you're trying to encode in single label stack, I assume you could easily hit number of entries NPU is capable of pushing. So I think you need to take into consideration what PC can do in terms of computing segment routing paths.
Right. Now, I think the amount of labels you can push at a source is very different from the amount of labels you might be able to push at a transit. So in general, the sources, it's out on a server, and a server can push pretty much anything because it's building the first packet. That said, if you do have limitations, yes, it's important that the controller or the PCE knows what those limitations are, and then can build using the loose hops, smaller label stacks, have them expand as they go.
So I think it would be useful to define what you do if your MSD is lower than number of labels you can push, and how do you segment routing tunnel to the next device which can push the missing labels.
Right, right.
So Keyur Patel, Arcus, I just wanted to clarify the question that Ali asked. I think it's the function of auto discovery within the AS, and then how you go about figuring out discrepancies should be a matter of local implementation, whether you choose to log, implement a timer, whatever it is, right?
Yeah, yeah. I think we can add some clarification that it is a matter of local implementation. So quick, let's move on before AC gets there.
AC Lyndon again. I hate to go back to this SRT, but your
okay,
SRT.
Then don't.
Oh, I will, but anyway. So what you're envisioning is the same way where you advertise the tunnel end cap and a color, and then you only need when that changes, the gateways only need to advertise that tunnel end cap and none of the prefixes that resolve on top of it, right?
Yes.
Okay, good.
So Adrian, I guess you have an answer to one of the questions. The interest by the...
There's certainly Bess is interested. Does that mean Bess wants to pursue it?
We'll discuss that on the list.
Okay, and yeah.
Next presentation.
The next presentation is unfortunately me, and I'm probably going to go mad. The next document is a BGP for service function chaining document, which I presented this morning in SFC. And now I've done the data center one. I'm going back to this one, and I'm going to get confused.
You should manage.
Great. So service function chaining is obviously done in service function chaining working group, but they are not chartered to do data planes at the moment. Shit. See, I said they are not chartered to do control planes. They are chartered to do data planes. Where here in Bess, there's a specific line item in the charter for control plane for SFC. So what we wanted to do was use BGP to discover the service function forwarders, learn which service functions are supported by each forwarder, and then distribute the information about the service function paths. Essentially, this builds on the BGP VPN methodology and tries to learn the lessons that were somewhat painfully learned as VPNs were being invented. and to fully support the work that is being done in SFC. Along the way, we end up creating multiple service function chain overlay networks, which are not dissimilar to the way you might support multiple VPNs over the same underlay. So, basic things. We use BGP to advertise using a new AFI-SAFI for two different route types. The service function forwarder and service function discovery goes in one route type, and the path exposition goes in the other route type. We build our overlay networks basically using route target, so that we can choose whether or not to import, and we have defined a type for the service functions, which requires a new IANA registry. And the last two bullets say what I've already said. So these two new routes that get advertised in the AFI-SAFI. The first one, service function instant route, says, I'm a service function forwarder, and I provide access to a service function of a particular type. And once all of these have been advertised, then somebody who's participating in BGP can see all of the service function instances in the whole network and know where they're located. So the advertisement's got the route target, of course, and that is identifying the overlay network, the service function network. It's got a route distinguisher, which is identifying the advertisement and therefore the service function instance, and the type of that instance comes along as well. So if you want to point at a service function instance, you grab the route distinguisher and the service function type, and that is the instance.
I did know.
Yeah, a little bell on it. We should give all presenters a bell. Let's go ding and right. So the other route that's advertised is the path itself. So the paths are built by controllers. This is a centralized system, service function chaining. So all of the information about the routes that the service functions that exist have been propagated out. The controller can collect all that and work out a good path. And a path is just a sequence of service function instances. So we can advertise this with, well, a route target to tell us which overlay network we're in, a route distinguisher so that we can actually know about the advertisement and refer to it. The service path identifier, the SPI, is an identifier that goes in the data plane, in the forwarding plane, defined by SFC, and then a series of hops, and the hops are encoded as TLVs. On the next slide, yes. So there's one hop TLV for each hop. That seems reasonable, and each TLV contains a service index. Now the service index is used in the SFC forwarding plane to identify the hop. It includes the service function type to tell us what type of service function we want to perform at that hop, and it's got the route distinguisher that was advertised when that service function instance was advertised. So back 2 slides, that identifier. So in the really uncomplicated case, the path is just a series of hop TLVs, each with one service function type and service function instance route distinguisher, and we're done. So here is a simple example. And we can see 3 service function forwarders, each advertising service function instance routes. The different color blocks are different types of service function. So we can see SFF1 on the left there advertises 3 service functions 2 of them are orange and 1 of them is blue, and they all have different route distinguishers. And I've chosen to use in the example, the route distinguisher that's IP address plus number. And then at the bottom, the controller is talking upwards and saying, well, I've got these service function paths across my network, 2 of them, and the left-hand one is the red trail through the network. And that's built of, well, the route distinguisher, which is really the controller saying this is the path, the SPI that will be used in the forwarding plane, and then the 3 hops to traverse along the way. And those show up as the service index, which decrements as you go, the service function type, which is the color, and then the route distinguisher of the original advertisement. So we've added some extra stuff because it's cool and we can, and it really helps. One of the things is to allow a hop TLV to have multiple choices of at each hop. So you can do load balancing and you can choose between different service functions along the way. And you can make that choice completely open so that the network is choosing, it's kind of delegated choice, or you can make it more restricted. We can also put in the path explicit control, and what we've done is we've chopped out a piece of our IANA registry for service function types and said these are special purpose service function types, which is very, very similar to MPLS with special purpose labels. So one of these types we've defined meaning change sequence, and that just gives you the instruction to, instead of just decrement the index as you go, to loop round or jump round or branch to another service function path. We also allow the inclusion of a tunnel encapsulation attribute so that the service function forwarders know how to reach each other across the core network, how to encapsulate into a tunnel to get to the next hop. And we allow you to associate service function paths with each other. And that's particularly helpful for bidirectional paths, but you could see all sorts of possibilities for protection and load sharing and so on in the future. So a slide of points of contention. Does this belong in Bess or SFC? I think it belongs here, but must socialize in SFC, and that's what I was doing this morning, and I expect it will go on being socialized that way. Do we support, we were asked, do we support looping, jumping, branching, and spiraling, which is a nice concept? And yes, all of this is defined in the SFC working group and in their architecture. And yes, this control plane solution addresses it. There is a danger of infinite loops inherent in the SFC work. In a sense, that's a responsibility of the controller to make sure it doesn't happen when it builds a path. But the SFC guys, I think, are going to be looking at what else they can do to detect loops. There's been lots of discussion now on the mailing lists, and some of that's been cross-posted to Bess from SFC, and some of it's just on SFC. Questions about who decrements the SI, how much does the SI get decremented by? Those questions are out of scope, both of Bess and of this control plane work. Okay, that's just, the control plane just works. And it's up to the SFC architecture and those guys to work out who decrements what, where the responsibilities lie. And another question has been, who does reclassification? So classification in service function chaining is the process of working out for a particular flow what chain you're going to put it on and how you set the next value of SPI and SI. And The control plane solution supports anything. The SFC architecture has specific views on this, and quite a lot of our assumption is that reclassification might happen at various points for various reasons, and that is largely speaking local policy. And there was a question, I think it was sent to the Bess list, about how we relate to the control plane work, the control plane requirements work in the SFC working group. And the answer is, well, obviously they've done requirements, and we strive to be consistent with those. We believe we are compatible. They asked me this morning to try and put in some pointers to which pieces of their requirements draft we're actually addressing, because there's quite a broad document. I think 9 is the total.
Wow.
There we go. So, questions?
Okay, I think I haven't been listened twice. Now I understand more about it. So basically, I understand that each service function forwarder is a BGP speaker, but actually that the BGP speaker talk to the peer is controller. It's not the other service function forwarder BGP speaker. Because really, other forwarder no need to learn whatever this.
No, wrong. Because when you're a forwarder, you need to know what the next hop on a path is. That you get from the controller, but you need to also know where that next hop is. So you need to be aware of the other service function forwarders in your network, and what underlay tunnel to use to reach them.
So my understanding is that this discover, it's information advertised, but the controller is the one to decide for each service function path, which service instance to use. Then that's informed to the service function forwarder.
Yeah. So the path is built by the controller, and informed to the forwarders. Yes.
So that's just informal, but not the help to see how you reach there. So that's still through the.
Right. Absolutely.
Okay.
Have you read the draft, Mr. Bryant?
Yes. You don't actually need, of course, the controller. You can do the whole thing as a distributed system if you want.
Yeah. You could entirely distribute, although it's a little unclear what the meaning of a service function path is if the entire decision is delegated to the network. Because you have to know which functions you want to execute.
Yeah, but you could put that knowledge on the ingress grooming sort of system that looks at a packet, makes a decision, and then.
Okay, so that's not
fully in sort of traditional.
That's not fully distributed. That's the partially distributed model that we used to have in MPLS traffic engineering before we invented central computation. Yeah, so certainly you can be doing that. Essentially, the classifier could be the controller. Yeah. However, you probably need to go to the SFC working group if you want to talk heresy. Any more? No? So you'll notice I didn't say, please can we adopt this as a working group draft?
Who has read the document?
Only half of it.
The good half or the bad half?
I guess the good half. AC Lindum. So the assumption is the controller computes the complete path identified by the SPI, and it never changes through the course of the packet's life that's traversing that path.
So it's
and the SP and the SIs are only unique within the indexes are only SFIs, I guess it's called, are only unique within the context of that SPI, right? So the controller is omniscient.
So the controller is omniscient within its overlay network. Yes. Yeah.
Ali, it's your turn.
All right. So let me start by asking, this is an incremental work to EVPN VPWS. And with EVPN VPWS, which is intended for point-to-point services, there was one area that was not covered, and this draft is to address that one. So next slide. So if you look at the current situation, we have EVPN VPWS draft, which has been around for 2-3 years. And that talks about point-to-point connectivity between attachment circuits at 2 different PEs. And the connectivity is basically between ACs. And these ACs can be either port or port comma VLAN or port comma group of VLANs. What we couldn't do before with the EVPN VPWS is to be able to have these point-to-point service tunnel and be able to aggregate bunch of ACs across different physical interfaces. And some customers came and asked for this feature explicitly because they wanted to use fewer service tunnel going through their core network. This draft talks about how we can do such aggregation. And basically, the current EVPN VPWS with each EC, we signal via BGP to the other PEs. So for every port comma VLAN, basically, we do that signaling. And if there is a failure of that AC, then we draw the corresponding EVPN route. Next slide, please. As I mentioned, what is needed is to reduce the number of the service tunnels in case we need to aggregate a bunch of the ACs across different physical interfaces. And to reduce BGP signaling associated with it as much as possible and be able to support all active and single active multi-homing. Next slide. So this is one example or one use case where we are talking about the VLAN unaware FXC, where we got the service tunnel between the 2 PEs. And you can see that in that service tunnel, we are muxing a bunch of ACs across different physical interfaces. Because we are muxing VLANs across different physical interfaces, these VLANs can be overlapping VLANs. So 2 things we need to do. First, we need to normalize these VLAN IDs to take care of the overlapping address spaces. And second, we need to have a with table to do the lookup on the disposition side, so we know which interface to send it to. So in this case, the reason we call it VLAN unaware because we are not signaling any of the attachment circuits or VLAN across the network. we just normalize the width and assume that normalized width space is the same across all PEs. If there is a failure, let's say if on the left-hand side, if the CE interface to the PE fails, we're not going to signal that. The only way we're going to signal it, because this tunnel is used for the all the ACs across all interfaces, and we're not signaling individual VLANs. And the way that the only way we tear the tunnel, the service tunnel down, is when all the ACs on all those interfaces fail. Next slide. This is another example showing that if we have we want to send different VLANs to different PEs, and we want to do that basically without any signaling. We are going to be using these VLAN unaware mode of FXCs, and this is basically showing pair of PE. You need one such service tunnel. Next slide. Now the other mode is okay. I want to be able to signal the. I want to be able to, especially when you have a multi-homing scenario where the CE is multi-home to PE1 and PE2. In such case of multi-homing, then it basically necessitates the need for signaling, because if one of your interfaces fails and you have a bunch of attachment circuit on that, and you don't signaling to the far end that you have that failure, and you those failure impacts these specific VLANs, your traffic is going to get, you're going to send it to the load balance it between the PE1 and PE2, and once it arrives, once it arrives from PE3 to PE1, it's going to get black hole. So for such a scenario, we need VLAN aware mode of FXC, and in there we are gonna again we are normalizing the widths, and we are gonna be signaling these normalized widths as a service IDs. It is one-to-one mapping, and all of these we're gonna be signaling it via a single service tunnel. So you have all these widths associated with a single MPLS service tunnel. And in case of the difference between this case and the previous case is, in this case, the service IDs are the same as normalized widths, whereas in the previous case, the service ID, it was its own unique ID, unrelated to the widths. And if there is a failure in this case, that failure gets signaled to the far end, and the far end knows that with these set of widths, you have it has lost one of the BGP next hop, and is going to adjust its path list to direct the traffic or forward the traffic accordingly. All right, next slide. This shows that you know, if I have multiple PEs and if the traffic needs to go with this mode of operation, how does it work? And is basically, again, it is one service tunnel per pair of PE. Next slide. Now, if we don't want to use, if we don't want to signal each individual VLAN. And at the same time, we want to be able to take care of the failure scenarios. Then there's a trade-off here, and the trade-off is at the expense of introducing more service tunnels, as shown in here. I can skip the signaling of the individual VLANs. So this is VLAN unaware mode for dual homing. It shows that how we can use VLAN unaware mode of FXC for multi-homing and take care of the failure scenario. But you can see the difference between this and the previous slide, that now I'm, instead of using one pair of service tunnel per PE, I'm using multiple pair of service tunnels. Next slide. The failure handling, as I mentioned, is very similar to the baseline EVP and VPWS. In case of when there is upon the failure of an interface or a PE, we send a mass withdraw associated with the corresponding interface to all the remote PEs, and all the remote PEs will remove that affected PE from the path list. Next. So this draft has been around, I think, for 2-3 IETF, and several vendors, they've already implemented it. So that's interesting, that although it's an individual draft, because of the requirement we got from a customer who's common across multiple vendors, we've implemented it, and as such, we are requesting for working group call for this. Any questions?
Iftikhar, Infinera. If you go back to slide number 3, maybe there's a picture.
Sure. Which slide?
Previous one. Previous one. Yeah.
This one or the previous?
Yeah. So is it a typo? You have a pseudo wire ID here. What is it?
That's a typo. That's the cut and paste. So I removed all the pseudo wires ID because in EVPN we don't use pseudo wires. We use service ID.
I think, yeah, this was my general comment. I think I saw this from the last ITF also. So
right.
There was a confusion what you presented and what was in the draft.
Right.
So the terms were completely not matching what's specified. So, for example, again, like this is another example.
So if you go to the, can we go to the previous one? If you go to all the figures, there is no pseudo wire ID. So you catch one figure with that pseudo wire ID. I try to clean it up. So in the draft, there shouldn't be any mention of pseudo wire ID. It should mention service ID. But if you see that, let me know.
Okay. Yeah, it will be good to also, the last time I read the draft, just a general comment for readability.
Okay.
I think it will be good to elaborate a little bit further the concept of service tunnel. It was still not clear.
Okay.
You know.
That's fine. So send me a note. Make sure I'm not forgetting it. I'll try to clarify it further.
Also, a little bit, for example, more.
So the service tunnel is basically that point-to-point tunnel.
Why? Okay, yeah, I think
it is equivalent to the pseudo wire ID,
exactly.
Right? It is equivalent to a pseudo wire.
I understand. I don't want to go to that route. I'm saying it will be good to actually, if you can explain that in the draft, and also, I feel like
so
some of the.
Let me suggest another thing. Okay. The area in which you think is not clear, please suggest text. Provide me with some text. Tell me if it is not clear, how we can clarify.
Okay.
Because that way, I know exactly which area you're talking about.
Yeah, another one is, I'll send you some comments. Yeah.
Sounds good. Thank you.
Just this figure, a little bit confused. So you have the weight PE, you have a weight table there, then you have a weight table on the PE2,
Yeah.
then you have a WRF. what did you exactly try to? There's
Oh.
two PEs, right?
Well, the purpose of this slide was to confuse you.
Exactly, you achieved.
So it shows that the endpoints, the termination points, doesn't need to be attachment circuit. It can be VRF. Okay, it can be anything on that. So the service tunnel doesn't need to necessarily on that end to go to a AC, to a physical interface. It can get terminated into the VRF.
So there's no WRF on this PE1.
Yeah. So on the PE, we are backhauling traffic from PE1. This is like one example that you backhaul traffic from your access network and you bring it and you terminate it into your POP or data center. Mr. Shah.
Yes, I want to express the same point that Iftikhar made, which is, I mean, I also read it a couple of times and found it a little bit confusing, so I will suggest some text.
Oh, that would be perfect.
Okay.
Thank you. Okay. So question to the chair, you're gonna pull the, ask the working group for the
On the list.
input on the
Yeah.
list, right? Okay, very good. All right, I guess next one, right?
It's loading.
So did I use your 5 minutes or still I have a couple of minutes? Thanks for giving me that 5 minutes. Okay. Although, yeah, you can find right on this first slide a couple of arrows. You know, Mr. Kayur is no longer with Cisco, although it feels like he's with Cisco. So, these are the author. Let's go to the next slide. Last IETF, we talked about some of the issues we had with the IGMP proxy when it comes to the all-active multi-homing. And we talked about at the very high level, we talked about a couple of areas that we are looking into. And what we did between last IETF and this IETF, we nailed on the proposed solution. And thanks to John Drake, a lot of the stuff is from his contribution. So next slide. So if you look at multi-homing issue, the question becomes when it comes to IGMP proxy, handling of the IGMP proxy when the CE is multi-home in an all-active redundancy mode. How do we synchronize IGMP joiner state among the P's in the redundancy group, and how do we synchronize the last member query among or the leave among the P's in the redundancy group? Given that because you have all active multi-homing, this is over LACP, over lag. It can get, the join and leave can get hashed into different PEs. And that is shown in the next slide. If you go to the next slide. So this slide shows that I have I'm connecting the CE2 via lag to PE1, PE2, PE3. And the PE2 is a designated forwarder for that lag. And join messages gets hashed and it comes to PE1 and PE3, but not PE2, even though PE2 is a DF and PE2 needs to send the PE2 needs to notify the remote PEs that it has interest in receiving the multicast traffic. So how do we take care of this situation? And next slide. And also, as I mentioned, same thing happens with the leave. The leave, again, in here, PE2 is a DF, and leave comes to PE3, and PE3 can send the last member query and expects a join, and the join arrives at some other PE. Because again, this is lag, the information can get hashed to any PE. So how do we take care of this scenario? The concept is very easy in here. You use BGP to rescue you, and because in EVPN it is, we have this capability built in. I use BGP for a lot of discovery and a lot of the route advertisement. This fits right along the path, and we are basically using BGP to synchronize these two things. Next slide. So we are introducing two new messages in BGP to synchronize IGMP and leave. Once this information is synchronized, then the PE that is a DF knows when to send when to advertise its interest to the other remote PEs. And as I mentioned, we are defining two new EVPN routes, one for synchronizing IGMP join and one for synchronizing IGMP leave messages. Next slide. For the synchronizing IGMP join, the principle is, again, pretty simple. The text in here, this slide and the next slide gets into a bit of details, but it works as follows: that when a PE receives a join message, is gonna create a local state for that join, and is gonna advertise it to the other PEs in that redundancy group, and the PEs that the DFPE, designated forwarded PE, that gets this a state IGMP join a state, either locally or via the message it receives from one of the other PEs. It now knows that there is a IGMP joiner state, and it now knows that it can let the remote PEs know that there is an interest in that membership. Next slide. And when a PE deletes its local IGMP joiner state, it basically withdraws its IGMP join sync. When another PE receives that withdraw message, withdraw IGMP join sync, it removes that route for that PE, and if there is no local join, it knows that there is no more no state associated with it, and it deletes its IGMP joiner state. And if the DF has no IGMP joiner state, then it basically withdraws its interest for that multicast group. Next slide, please. The message in IGMP join, as well as IGMP join sync route and IGMP leave sync route, they are very close to the previously defined message, the SMET route message, which the PE sends to indicate that it has an interest. The difference is in here, there is one additional field, and it is Ethernet segment. Okay, so these IGMP join sync and IGMP leave sync route, they are exchanged among the PEs in a redundancy group. Whereas the SMET route, you advertise it to the remote PEs, letting them know that you have an interest for that multicast group, and it gets sent by the DF in that redundancy group. So that's the differentiation. Next slide. Now, when it comes to the synchronizing IGMP leave, when a PE, DF or non-DF, receive a local IGMP leave message, it initiates the leave procedure regardless whether it has a join state or not. And it starts a max response timer and initiates, and it sends the last member query. It also advertises the IGMP leave sync route to the other member of PE, so that the other PEs also start their max response timer. So when a PE, DF or non-DF, receives the IGMP leave sync, again, it is, as I mentioned, it starts a max response timer. And next slide, please. If one of the PE receives a local join before the timer expires, then it advertises the join message to the other guys. And if it doesn't have if one of the multi-homing PE receives an IGMP join sync route, then it creates the IGMP join state. Next slide. And when the max response timer expires, the PE that advertised the IGMP sync route, IGMP leave route, it withdraws it, and any other PEs, any other multi-homing PEs for that Ethernet segment that they started the max timer, if they haven't received any IGMP join messages, whether local or remote, it deletes the IGMP join state. And if it the DF, if that PE, if the DFP has no more IGMP state, is going to withdraw the SMET route. So it basically, we introduced two messages for making sure that everybody sees the same IGMP join and leave state that comes from the CE. Next slide. As you can see, the IGMP leave sync is also very similar to the join, and also very similar to SMET. And except the difference between this and the SMET, it has the Ethernet segment identifier. Next. These are some additional extended community flag that it is under discussions. Next slide. And we introduce one new AVI RT extended community, and the draft discusses why we need this new extended community. Next slide. So conceptually, this is a simple draft. As I mentioned, we are introducing two EVPN routes, one for the join, one for the leave, to synchronize these join leave messages coming from CE among the member PEs. And again, this is another draft that a couple of vendors are working on it, and it's been around for few IETFs, and I also like to request for a working group call on that one. Okay, now time for questions.
Yeah, Lucia from Huawei. I think that's the join and the leave message from CE to the PE. That message you have to advertise in the entire domain, so you can use that to resolve the designated PE. Only the query.
Okay.
If the designated PE query to the CE about the information needs to synchronize.
This is exactly what we are trying to avoid, because we are trying, by using the proxy, We don't want to, you're going to get tons of join messages. You don't want to advertise, flood the network with all these join messages. You want to advertise only one. And the advertise, if you advertise, okay, only one to the remote PEs, then you want to make sure in terms of the state, you synchronize the state among the PEs in the redundancy group. So if you go through the draft, it gives the reasoning why we want to do these joint suppression. Just similar to the ARP suppression, that we don't want to flood the network, the core network for ARP messages, and we want to suppress it.
I see. So what you propose, basically, this multi-homing group will first gather the messages, then summarize the, all the join, then send to the network.
It sends it and it just suppress all the subsequent ones. Sends the first one and suppress the subsequent ones.
Jorge Rabadan,
right.
Nokia.
Yes.
We started to discuss, and I think we need to discuss more. But one comment though is about the join sync route and the leave sync route.
Right.
I think I understand the logic behind,
right.
And you're trying to mimic exactly the behavior of IGMP version 2 in BGP, but it's extremely expensive in terms of routes. I mean, you can have a lot of routes, S-G groups, so a lot of routes, and you are duplicating the amount of routes and the memory and RAID and the noise in BGP, right?
These are only limited to the PEs in the redundancy group. So if there are two, you're going to be limited to only those.
I understand it's only affecting the, with RT constraint, it's only affecting the PEs in the Ethernet segment, but it still can be potentially a lot of routes. So I don't see why you cannot use a single route to do both functions. So we can take it offline, but
sure, we can discuss it offline. Because of the ambiguity it creates, we decided because of the state, there are two different states. We need to, even if you send it, you have to have a flag to differentiate between the two.
Right.
And you're going to end up keeping it in the BGP table anyway, because there are going to be two different BGP
But you
routes.
can have a single BGP route in the RIP. Yeah, you need different flags to indicate if it is a join or a leave and all that. That I understand. But at the end of the day, what you need to do is to create a state, to synchronize it or to remove it, really.
Right, and there so both the join and the leave, they can come. They're completely independent, and you cannot couple them together. And if you think that we can use one single route to resolve the state, I will be all ears, and we can discuss it offline.
Sure, we can discuss it. And the other thing, can you go back to the slide with the leave sync route? Yeah. So out of curiosity, what is the leave group synchronization? The 4 octets that you have there. So those are not explained in the draft.
Leave group, this is the synchronization. I thought it did is an ID to making sure that the different you can identify different leave.
Oh, so is that kind of a sequence number?
Sequence number.
That you keep incrementing?
Yeah.
Oh, okay, I see. Thank you.
Sure.
Robert Rashuk. So one comment here is that the problem you are describing is extremely useful, I would say. And the solution, in my opinion, should be extended beyond EVPN. Because with basic beer, let's say, they are flooding the IGMP messages to everyone in the domain to actually do similar thing.
I see.
So I think maybe there's more discussion required to extend this beyond EVPN.
So very good point. Thank you, Robert. The EVPN, I think, EVPN is agnostic regarding the tunnel type. So I can use any kind of tunnel, including beer, but I think your point is very well taken that it needs to be mentioned explicitly, and probably we should also make sure that the beer working group is aware of this work as well.
If I have segment ID 10 octets, right, would not be useful in other cases.
Okay, thank you.
Clarification question?
Sure.
Himanshu from here. So if you have a P1, 2, and 3 in a redundancy group, and if P1 receives multiple joins, does it send out multiple sync to the P2 who's a DF, or just one?
So if it receives a multiple join, if it is for the same version, it's going to send just one.
Just one?
Yes.
Okay. So it has a local count, so only when he receives equal.
It has a state. If it receives because BGP is stateful, right? When it receives the first join, okay, it says it creates a state and it sends the BGP IGMP join sync route.
Yeah.
And because that's a stateful, everybody else has receives the route, keeps it, and it doesn't need to send subsequent BGP messages.
Okay.
Any more questions? All right, Mr. Sami, the floor is all yours.
What you've left him. What? Sami. Wasn't supposed to be a 5-minute presentation. 10 slides. Well, Ali managed to do 16 slides in 10 minutes. So.
Okay, yeah, sure. Okay, good afternoon. Yeah, this is Sami Boutros. This draft has been around for close to 4 years. So what we have in the slides here is simply a refresher. So we don't need really to go through all the slides, but we'll try to go quick through them. So this slide was as well for our group adoption in the summer, but unfortunately not so many people responded to the call because many as well didn't see it. So if you go to the next slide. So this is again a refresher. The draft is about interconnecting different VXLAN networks to via an MPLS core with the data plane learning done in the data plane learning done in the VXLAN network. So no control plane learning in the VXLAN network with the stitching here. Next slide, please. So here the draft is talking about how we are extending the intra layer 2 connectivity for a given subnet across the different sites, layer 2 sites with data plane MAC learning through the MPLS core, with some of them are VXLAN sites. And it does not preclude as well the support of IRB for inter-subnet connectivity. So this is the reference architecture showing the VXLAN network interconnected by an MPLS backbone and where BGP for EVPN is running, as shown here, is in the core of the network, given that the VXLAN or could be as well layer 2 sites, layer 2 VLAN sites. We are doing their data plane MAC learning, not control plane MAC learning for BGP. So here is a summary of the VPN routes used. So we are using still the MAC or the BMAC route if we are doing EVPN or PBB EVPN. We are using the Ethernet AD route as usual. One route here that's missing is the Ethernet segment route. We are using the Ethernet segment route for doing DF election as well for the multicast traffic because we need to do pair VNI DF election. So the inclusive multicast route as well is being used to set up the multicast connectivity across the different sites and through the core. The draft explain at length how can we stitch the IP multicast trees in the VXLAN network through the MPLS core using BGP. So yeah, this is again a refresher for how we handle the unicast traffic. The MAC address is being learned in data plane and are being distributed in control plane for EVPN or are being still learned in data plane if you are doing PBB EVPN. The unicast traffic will be encapsulated in the VXLAN network with the IP UDP stuff, but of course with the MPLS label in the MPLS network. And for redundancy, because of the data plane learning in the VXLAN site, we are proposing the use of an IP anycast address to avoid flip-flopping of the MAC address while maintaining still ECMP for the site, the VXLAN site to the MPLS core. For the multicast, again, we are talking about the stitching of the PIM build tree in the VXLAN site, for example, with the point to multi-point or multi-point to multi-point trees built in the MPLS core. And we have here in the MPLS core as well the option of doing ingress replication. The stitching, of course, must ensure no duplication and no loops. And we are going to be doing the stitching from the VXLAN side, the core, with what we say here per VNI. So meaning that the two PEs that are connecting the VXLAN side to the MPLS core are going to be doing DFL action and doing per VNI load balancing. Yeah, this slide is talking about some optimization with PIM-SM. So the idea here with PIM-SM, given that we may be receiving the multicast traffic from the two PEs connected to the site, PIM-SM may drop the packet because of the RPF check. So the draft goes through a proposal. For the sake of time, I'm not going to go through the proposal. It's listed in the draft to explain how can we solve that problem of dropping based on the RPF check. If we use PIM Binder, we don't have that RPF problem, but with PIM-SM, we have that problem. As we said in the previous slide, for stitching multicast, when we do the DFL action, we are doing it bidirectional, meaning that we block on both ways. Who is forwarding for a given VNI is forwarding on in a bidirectional way, meaning the PE that's assigned or is the DF for a given VNI is forwarding on both direction, while the other PE is blocking, of course. In here, when we are using PIM-SM, the proposal is that we are not going to be blocking from site to core anything similar to regular EVPN with multi-chassis lag, in which multicast traffic is allowed from any leg of the lag when it's coming from site to core, but we block only from core to site. So this is going back to that mechanism. While in the previous slide when we were discussing the PIM Binder, we were blocking in both directions, meaning from site to core and from core to site. Next slide. The draft as well talk about some use cases. So the use cases here, includes a homogeneous network interconnect. This is with few VNI models, the bundle service, the base model, and even VNI translation to do normalization across different sites that are under different administrative domain. As well, it's talking about heterogeneous network in which one side could be VLAN, the other side could be VXLAN. Okay, next slide. Yeah. So yeah, the draft is definitely being planned or is already in development by some of the vendors that some of them I used to work for, and this is why we are asking for work group adoption, right? Sure. Go ahead. Question.
Yeah. Jorge Rabadan, Nokia. For the multi-homing thing,
What's that?
for multi-homing,
Uh-huh.
because you're using this Anycast VTEP towards the VXLAN side,
Correct.
but I assume towards EVPN you're still using different BGP stops, right?
Correct, correct.
Okay. Maybe obvious, but I couldn't, I mean, it would be nice to clarify.
Sure.
And also that you advertise the MAC addresses with the Ethernet segment identifier of the
True.
VNI.
Yeah,
maybe,
how exactly we are gonna be setting the ESI and so
yeah,
on.
maybe worth clarifying how they exactly.
Would you mind sending those comments to the list?
Yeah, I can. Yeah, sure. Thank you.
Thank you.
Hello, just one question. I think
Sure.
also related to the multi-homing.
Yeah.
So for this VXLAN to connect to this EVPN, is this multi-homing behavior exactly same as a VLAN multi-homing case?
Yeah, it's similar. It's similar to the VLAN or the multi-chassis lag. I guess what you mean is multi-chassis lag multi-homing. Yeah, it's similar to the multi-chassis lag multi-homing. The difference, as we said, if you ignore the PMSM optimization, the difference is that we are blocking bidirectional. You know, with the multi-chassis lag, you don't block multicast coming from the multi-chassis lag to the core. You block only from the core to the multi-chassis lag. You see what I mean? So here with VNI, sorry, with VXLAN, we block both ways.
Yeah. So this draft we have already pulled it on the for adoption. Did you?
Correct, but many people, you know, didn't.
Yeah. No. So whatever the reasons. So and we decided not to adopt it because there is really not enough support for that. In case we effectively repoll it in some near future, we need to make sure there is support. Otherwise, we won't keep on going.
Repolling it? Yeah, sure. So let's try to repoll it one more time.
Okay.
So yeah, I think we have two other drafts here. They are related to auto provisioning or automatically provisioning some network or simplifying the provisioning in one way. So this is the first draft here. This is the auto provisioning. Okay, this is EVPN auto provisioning draft. Next slide. So what the draft is about is that how can we provision a network using EVPN? So we provision services and using EVPN as a protocol to allow us to do so. The idea here is that this is a network with a controller, and EVPN here is going to be used to trigger the provisioning of the network based on first sign of life. So next slide. So as shown here, we have a controller to that network, and we have the whatever, you know, this could be in a data center, this could be TORs, XSPs, and so on. What's going to happen is that when the XSP is going to be receiving on his trunk ports a first sign of life packet, right? He's going to be creating or gleaning from that packet information that he's going to be setting up an EVPN MAC IP advertisement to a controller with. So he's going to be setting in that EVPN MAC advertisement the ESI field. He's going to be setting the IP and MAC fields, and the controllers basically is going to be checking those fields against a pre-provision policy for the network, and then is going to be pushing that information down to the different boxes that exist in that network to realize the service. So that service could be a layer 2 service or a layer 3 service. And EVPN here is being used as a protocol to trigger that provisioning from a controller down to the network. That first sign of life, as we said, could be a regular packet, an OR packet, or whatever packet that we can glean information from about the subscriber and inform the controller about. The first sign of life as well could be even an inclusive multicast packet received from an EVPN PE or NVE to another EVPN PE or NVE. Next slide, please.
Excuse me. One quick question on this slide. You just said that the first sign of life packet could be received inclusive multicast route.
Correct.
Is that from the core side or from the servers?
The inclusive multicast, no, will be from the boxes, from the routers.
From the access PE1 or?
Correct.
Received from access PE2 or?
Exactly.
So why wouldn't access PE2 send that, have sent that to the controller, and then I thought the controller will figure out all the
thing. Oh, that scenario exactly. How will it work? The idea here is that the first sign of life, if it is coming from the server, right?
Yeah.
Yes, it's going to be pushed to the controller. The controller can figure out from it that he need to push to a given box or a given set of boxes an EVPN service to be configured, right?
Right.
But as well, there could be a box in the network that could receive still, can be importing some inclusive multicast route and will only be enabling that service based on the trigger. So, I mean, to discuss the exact use case for that, maybe you can discuss that offline if you like.
Oh, okay. Yeah. So maybe you could.
We need to clarify more about that. I agree.
Yeah.
So, next slide. So this is ESI encoding to allow for that first sign of life communication. So what we are proposing is that the access PE who's going to be receiving the information from the server can glean the Ethernet port on which he's received the information on, and as well can glean some of the VLAN information that exists on the packet, given that he is going to be connected with a trunk service to the server, and this will be the information that will be sent over to the controller.
Excuse me, one more question on this slide. So instead of encoding in the ESI, could it be encoded in an extended community? Would that be more flexible?
We definitely are open to that too, but I think what we have currently in the draft is that use the ESI as an encoder, encoding the information in the ESI with a new type for that ESI. But sure, you know, if you won't mind sending all those comments as well, the previous one and this one will be great. Thank you. Next slide. So that's about it. We think the author saying that it's a good function to be added, or good use of EVPN to trigger an auto provisioning of a network through a controller. So we feel there is value in it, and we are definitely seeking input from our group on the idea on what can be done with it. Any more questions? Maybe it's the last one.
No, you have 1 minute less, so you don't have time to do a meaningful presentation.
Okay.
Okay.
Thank you.
Thank you very much, everyone. Thanks for your interest and participation, and see you Chicago. Thank you. Hey, blue sheets. I haven't made a call for that during the meeting. They are somewhere. If you haven't signed them, please do so. It is important.
You're all set, right? You're all set.
Alia?
You started with the V2 and take care of the V2 and V3.